Okay, so let me put my own time here. Is there a pointer? So, okay. So, okay, well, my name is Arturo Núñez Castiñeira, and I'm going to talk to you about cosmic ray diffusion that we've been hearing quite a lot today, but in simulations of an isolated galaxy with full MHD. This is a work that I've been doing as a postdoc in COA with a team of both observers and simulators. Now, what are we doing? As I said, what we're doing is a simulation of a isolated galaxy with the code Ramses, which is an AMR code where we're solving MHD equations coupled with gravity, some subgrid physics to take care of the stars. So basically, there are some stars particles that are born when the gas collapses. Once you have some gas conditions that bake the stars, these stars are alive and they become supernova, which is where we're going to inject this last ingredient, which is the cosmic ray fluid. Why are we doing this? Basically, if you look at the galaxy if you simplify what a galaxy is, it's just a system, a very complex system where gravitational collapse is competing with local pressures. And what observation seems to point out, particularly local observations, is that the typical pressures have more or less equipartition between thermal, magnetic, turbulent pressure, and cosmic rays. So it's probably a very important ingredient for the evolution of the galaxy to include cosmic rays. So this is what we're doing it. Now, what are we doing? We're basically simulating a dwarf galaxy with a total mass of 10 to the 11, with a very high resolution of 9 parsec resolution, which is still, I mean, it's high resolution for simulations, but for modeling the evolution of particles as cosmic rays, it's very coarse resolution. We're also resolving the ISM. I'm going to tell you a bit more about that. And we take the cosmic ray as a fluid of cosmic rays that corresponds to the low energy range. So this is GeV range. The idea is that we are going to propagate it following two versions of a diffusive cosmic rays. One in which the cosmic rays are basically diffusing in an isotropic way, and another one in which they are anisotropic, meaning that they follow a little bit the magnetic field lines. The values that we take for the diffusion coefficient are spanning between 10 to the 27 and 10 to the 29, so we can bracket values that are predicted for the Milky Way, and also we can compare with other simulations. So basically, also the energy that is injected is 10% of the supernova. So one of the things that it's very new for our simulations, that it could be very important, is that the gas evolution of the simulation is typically simplified in other simulations by imposing this pressure floor, in which basically you put a frontier below which the gas cannot go, a frontier in pressure. And the result of this is basically that you're not creating this phase here, which is the cold neutral phase. What I'm showing you here is the pressure and density. So this is a 2D histogram of the galactic gas. And by doing this pressure floor, you're basically erasing the cold neutral medium, which is the medium where the stars are born. So you're making simulations forming stars in odd places. So what we did was to update the gas physics of the simulations and get away from, take away this pressure floor, so we can actually populate the gas in a more consistent way. This method is basically validated with higher resolution simulations. Now, one of the nicest results of this is that we managed to recover mass fractions for the different phases that are more or less in agreement with what is observed in the Milky Way. So these points here are observations in the Milky Way with very big error bars, because these are quite complicated observations. So for now, we're very well in the park, but we're not able to disentangle yet between the different coefficients, at least not with this observable. So what's the result? These are the 6 galaxies with simulation. This is the density of the gas. So what you see on the top are the 3 anisotropic diffusion simulations and the 3 isotropic in the bottom. And the kappa parameter is basically growing as you go to the right, okay? So this is 10 to the 29. As you can see, if you look at an overall, a very quick look, this is not a good way of disentangle. The gas is more or less the same. There are some small differences, but it's not very efficient. You can also look at the cosmic ray distribution, just as an example. As you can see, when you do anisotropic diffusion, your cosmic ray structure is following a little bit the galactic arms. So you see more or less the structures. And as you put a higher kappa, so higher diffusivity, more efficiently escaping cosmic rays, these structures are washed out. You can also look at the isotropic diffusion, in which you get these little blobs. And well, but this is the situation. Now, okay, so one interesting result is basically, as I said, there is expected to have, we're expecting to have in a galaxy some sort of equipartition on the same amount of pressure. So here, for different pressure components of the galaxy. So here I'm showing you the radial profile. So this is the radius of our galaxy of different pressures, magnetic, thermal, cosmic rays, and kinetic or turbulent. And we see they are more or less in the same order of magnitude, except for these two cases, where very interestingly, the magnetic pressure, it's quite low. It's almost an order of magnitude low, particularly in the center. This is due to some sort of a plateau or a stop in the magnetic amplification of the galaxy. What happens here is basically that this stop of the magnetic amplification basically boosts the star formation. So here you have the star formation and the time of evolution of the different galaxies. And the two galaxies with a higher star formation rate are exactly the two galaxies that, as here are the maps of the magnetic field, are the two galaxies that at some point stop amplifying the magnetic field, and basically this took away an extra pressure. The magnetic pressure is no longer there. In the other cases where the magnetic pressure is there, so notably all the anisotropic cases, the star formation is very well suppressed, which is very, very much interesting to control a little bit the magnetic, the stellar component of the galaxy. Now, what this is evidencing, what this is showing is that there is some sort of dual effect of the cosmic rays on the fact that we have cosmic rays that diffuse differently on the star formation rate of the galaxy. Not only by the fact that in these cases, when you have higher diffusion, you're going to have less cosmic rays because they're escaping, but also you're going to have less magnetic field pressure, which will make a double effect on the star formation effect, on the star formation rate of the galaxy. Sorry. Now, another interesting way of basically looking of your simulations and comparing it with observations is to look at the gamma luminosity with respect to the star formation rate, for which we have some observation. Here I'm showing it divided by the star formation rate. So here we have a lot of observations of galaxies that are more or less well behaved. There are two or three galaxies that are that you could place more or less here, but they are thought to have an AGN, so we take them out because this, the presence of an AGN is of course going to drive the gamma luminosity up. And if we put our galaxies here, what we see is that values that have a diffusion parameter close to that of what is inferred for the Milky Way are falling more or less into the ballpark, particularly for anisotropic diffusion. In the case of isotropic diffusion, what we get is basically very, very slow isotropic diffusion. It's consistent with observations, while fast isotropic diffusion tends to get really, really far away from observation. So we are able to say that very fast isotropic diffusion are not really consistent with observation. Now there is a problem with this, and the problem with this is that other simulations tend to say the opposite. Typical simulations like those of Chan et al. In 2019 and Maria Berham, they tend to say that slowly diffusing cosmic ray in simulations yield a gamma luminosity that is quite above what is observed. And then once you do fastly diffusing cosmic rays in simulations, you are making galaxies that have a gamma luminosity that tends to agree with what is observed, which is not what we say. At least in our simulations, we recover agreement with observations in both ranges, no, by using diffusion parameters that are in agreement with what is predicted, and by comparing with other simulations, with other observations. Now, Now, of course, this has to be looked in more in detail because, yeah, this is the last one. This has to be looked more in detail, mainly because the gas physics on the simulations tends to be overlooked and overly simplified, which is something we didn't do in this case. So might be a point, but nevertheless, simulations exactly similar like ours, but with, let's say, the wrong gas physics, which are these points here with the cross, tend to give also, let's say, a compatible prediction for the gamma luminosity. So the picture might be more complex than we think, but nevertheless, I mean, what we see is that probably the kappa, the diffusion parameter should be around 10 to the 28 as typically predicted. So just to conclude, the diffusion, different diffusion scenarios modifies very weakly, as I said, the gas fraction of the different ISM phases, and also the main distribution of the gas in the galaxy. But we see that the different models have a dual effect on the star formation effect, particularly by modifying the magnetic distribution of the galaxy. So either this is happening at large scale, affecting the large dynamo, or at smaller scales, but there is an effect on the magnetic field that needs to be studied and understood. And finally, observations of gamma ray luminosity of local galaxies seems to point that our simulations with fastly, particularly isotropically diffusing cosmic rays, are not very consistent with what is observed. So we're planning on extending this study basically by doing a very detailed small-scale studies on our simulations and extending the set of simulations by adding a diffusion parameter that is not global, but there's my time. But it will rather depend on the ISM properties, which is probably more realistic to what's probably happening in the galaxy. So thank you, and if you have any questions.